All right, so now we're going to discuss the homology of a ball. Okay, so we're going to look at sort of a ball of BK. All right, so this is the set of points x in Rk with the property that the norm of x is less than or equal to 1. All right, and then we consider K, it's like a complex, simplicial complex that triangulates BK. Okay, and then we want to look at the homology groups associated with this. It's like when we were discussing homology groups, we said that intuitively what it does is that it measures the number of holes of various dimensions. So based on that intuition, you might expect that the homology, it's like of this ball, it's like it's trivial, and this is almost true. So the question is, well, what is the homology of the ball? Okay, and then so based on our intuition, that homology measures the number of holes right, you might expect that the homology groups are trivial for the ball. Okay, and this turns out to be almost true, right? So in fact, what happens is that if you look at the P homology group of this simplicial complex K, this is equal to 0 if P is not equal to 0. Okay, and then H0K is going to have rank 1, which means it's going to be Z mod 2Z. Okay, again with sort of Z2 coefficients, if you will. Okay, so it turns out that it's not so easy to prove that any complex that triangulates it's like this ball will indeed have these homology groups. So it takes a bit of work to do this. So showing this sort of is sort of non-trivial, surprisingly non-trivial. But we can at least attempt to show this. It's like for a particular complex which triangulates the ball. Okay, so let's just say, so let's consider the case where the complex K, right, it's just are the faces of a single P simplex. Okay. I'm sorry, K simplex, right? Okay. So the P chains of K, right, have rank equals to K plus 1 choose P plus 1. So this just follows the fact that when you have a single K simplex, they're actually there are K plus 1 vertices, right? And if you want to look at all possible sort of P simplices of this, right, you get to choose P plus 1 out of these K plus 1 vertices. And that would be a distinct face, distinct p-dimensional face, if you will. It's like of the single K simplex. So, all right. So let's write these things down. Okay. So if you have all right. So if you have again these single K simplex, right? You let the vertices be just say U0 all the way up to UK, all right? And then we consider a P chain with sort of simplices of the form UI0 all the way up to UIP. Okay, all right. And then let's try to see in this situation what the cycles look like and what the boundaries look like, right? So let's first look at the cycles. So the condition that you know a given P chain, let's call it C, right, is a cycle. Let's see, right, in the sort of in the chain group, if you will, a dimension P of K, right, is a cycle, right? It's basically obviously just that the boundary of this is equal to 0. So what does that mean, right? That means that every single P minus 1 simplex, right? So this implies that every P minus 1 simplex sort of shows up an even number of times as faces of the chain, right? Sort of P simplices in C. Okay, so again, it's like we're using Z2 coefficients, right? So, and in particular, if you have a sort of P minus 1 simplex, which is not a phase of any of these things, obviously it would just show up 0 times, but 0 is an even number. So this is a perfectly reasonable statement even in that situation. All right, so anyway, so if P is greater than 0, right, the claim is that we can construct a P plus 1 chain whose boundary is C, right? Let's call that P plus 1 chain D, right? Whose boundary at D is C. Okay. So if you can do that, obviously it's like that means that the P homology group is trivial, right? Because yeah, so that's yeah, so you know, in order, if we can show this, it's like then this would imply that the P homology group is trivial. So if we can show this, then HPK is 0. Okay. So how do you do this? Okay. Okay. So we let D, right, be the set of p plus 1 simplices of the following form. Okay, so U0, U0I, all the way up to UIP. Okay. So basically what happens is that I've, in some sense, added a point U0, right, to the P simplices, right? So these are the P simplices which, okay, if you didn't have the U0, this would be the P simplex which shows up. It's like in the chain C, right? And then I sort of added this point U0 to it, okay? So to see that, you know, C is the boundary of D, okay. Okay, what I do is the following. We need to distinguish, we need to consider three cases, if you will. Okay. So which have to do with these three types of P faces of simplices in D. Okay. So the first case is that you have a P simplex in C that does not contain U0. So in that situation, this occurs exactly once as a face of a P plus 1 simplex in D. Okay, and therefore belongs to the boundary of D. Okay. All right. Okay, so let's look at the other two cases. Okay, so case 2. So you have a P simplex, let's call that tau, which is not in C. This occurs an even number of times. Let's see. So once for each time the sort of P minus 1 face, sigma is obtained by dropping U0. each time this one occurs in the boundary of a simplex in C. Okay, all right. And then sort of the third case is that using sort of a similar argument, we get a P simplex tau in C that contains U0 an odd number of times. Because basically one of the P simplices, in C that contains a P minus 1 face, sigma does not give rise to a P plus 1 simplex in D, which is namely tau. Okay, so all right. So anyway, right. So basically, what that then shows you is that if you again choose this D sort of P plus 1 chain, it's like which is obtained by basically augmenting it's like all the it's like all the smaller simplices. It's like by this, then you get exactly what you need. So let me sort of give you maybe sort of an intuitive picture for what is going on, right? So imagine you have sort of just edges, okay? And you want to think of those edges, it's like as being the boundary or something, okay? So what you do basically is that you've added a new point, okay? And then now you have all these faces, okay? So let's just call that U0. So the basic idea is that you take this thing and you construct what is sometimes referred to as the cone of it, right? You take these points and you essentially, it's like homotope between those points, it's like and U0, okay? So this is exactly what we've been doing, right? If for every simplex, it's like in the p-dimensional chain, right? I've added a new point, okay? And then so in some cases, it's like that point is degenerate because it's already there, so you don't really get anything new, but that's okay, all right? So in any case, it's what you end up with is that you have something which looks like the cone, and of course the boundary of the cone is just sort of the original piece at the bottom, right? So that's sort of intuitively what is going on. It's like with this construction, it's like where you try to show that any it's like p greater than 0 chain, right, can come from the boundary of some higher chain. Okay, so this is sort of the cone construction, if you will. Right, and so that's sort of what's sort of intuitively happening here. Okay. All right. So anyway, so this covers the positive dimensions, right? And then, so that sort of tells you that every cycle, right? Every p cycle for p greater than 0 is a p boundary. So it's a boundary, right? So so you're good to go. All right, so this covers sort of the p greater than 0 case. and it shows that HPK is trivial. Okay, for the p equals 0 case, right, you can observe that exactly half the cycles are boundaries. So that tells you that sort of the zeroth homology group, right, which is of course just Z0 quotiented by B0, the cycles quotiented by the boundaries, right, is isomorphic to Z mod 2C, and the Betti number associated with that, which is the rank of H0K, is just 1, which is what we claim. Okay, all right. So I should also remark that you might have heard of the Poincare lemma, and the Poincare lemma. It's like the proof of the Poincare lemma is, can be shown. It's like using sort of a cone or cocone construction as well. All right. So let me just stop here for now.